Hey guys, so in this video I want to go over a problem using Coulomb's law. So I actually got this problem off MIT's Opencoureware. I'll provide a link on the website. But I wanted to do this problem because I thought conceptually it's a great problem, and if you guys ever wondered or heard that electric forces are a lot stronger than gravitational forces, this problem will explain why, and you'll actually see a numerical value of how strong electric forces are. So this problem starts off with having two dust particles floating in space. So maybe a little creative and draw some stars to set up the scenery. So I have two dust particles drawn as so, and they're separated by a distance of r, and what's given is the mass density of each particle. So if you guys didn't know, density is usually written with the Greek letter rho, and rho is given by 2.5 grams per centimeters cubed. The diameter of each dust particle is given as 50 micrometers. So this would be D. So due to Newton's universal gravitational law, we know that the particles will eventually collide with each other, given that there's no other forces acting on these objects, and if they were moving in space, they'd be moving at constant velocity, meaning no acceleration, so no force. So here's Newton's universal law of attraction. So as you can see, this law pretty much mirrors Coulomb's law, describing the force between two particles, and this law describes the attractive force between two objects. So I'm going to write gravitational below the F. So we know that the force, actually the gravitational force between the two particles are attractive, so they'll be pointing towards each other and in this fashion. And also, let me write the fact that m1 is equal to m2, so I can rewrite this gravitational force as g times m squared over r squared. If you didn't know what g was, g is a constant, just like the Coulomb constant in Coulomb's law. Now the problem asks, what if these dust particles picked up charge somehow? So these particles picked up an electron, just theoretically, and I want to figure out how many extra electrons do these dust particles need in order to cancel out this gravitational force pulling these particles together. If you recall Coulomb's law, I'm going to write out the law without any vectors. If we know that these two dust particles will take on the same sign of charge, we know that they're going to repel, so the electric force would actually point in the opposite direction as the gravitational attractive force. So if we're interested, when the electric force cancels out the gravitational attractive force, we just need to set the two equations equal. So I'm going to call this F electric, and I'll set it equal to F gravitational. I'll just put grav for short, and that's equal to, but the problem asks, how many extra electrons do I need to put on each dust particle? So if I have some electron and I wanted to put it on the dust particle, how many would I need to put on each dust particle in order to cancel out the gravitational attractive force? So let me rewrite the electric force, Coulomb's law, as follows. So the problem asks, how many extra electrons do I need to add on each particle in order to cancel out the gravitational force? So I can rewrite the electric force as follows. Some number of electrons on each particle. So if you could see that Q1, Q1 right here is actually this quantity, and this is represent one of the particles, and this Q2 is representing the charge on the other particle. So some number of electrons over the distance squared, and I still set that equal to the gravitational attractive force. I remember I said m1 is equal to m2, so I'll just call this m squared over r squared. So let's simplify this equation further. So I have n squared times e squared over r squared is equal to 4 pi epsilon naught times g m squared over r squared, and you cancel out the r squareds, solving for n. So if you noticed, I haven't plugged in any numbers, and this is how you want to approach every physics problem. You don't want to plug in numbers till the very end, because when dealing with numbers, you're more likely to make mistakes, and when you make mistakes, you're more likely to lose points, which is probably what you don't want. So a good problem solving strategy is to plug in numbers at the end, and you'll see actually how things cancel out. And you actually saw how I didn't need the distance between, I didn't need to know the distance between the two dust particles. So now let me just talk about how to find the mass of each particle. The density of each particle was given as 2.5, and then I knew the diameter. Mass can be defined as the density times the volume. So now all I need to worry about is finding volume. So in order to find the volume, I need to assume that the two dust particles are spherically symmetric. Well, based on what's given, that's my only assumption, because how else would I solve the problem? The only other way I know how to solve for volume is by integrating over some function x, y, and z, and multiply it by dV to get the volume of the object. But in this case, we don't have to assume this, and I don't ever recall running into a problem where I had to compute some complicated integral, because that's what math class is for. And physics, we're not so focused on the math, we want to focus on the concept. So volume of a sphere is defined as follows: 4/3 pi times the radius cubed, and we have d, which is diameter, so d over 2 is the radius. So let me rewrite the radius as 25 micrometers. Now by looking ahead, I see that this density is given as grams per centimeters cubed, and this is given in micrometers. And if I found the volume, I would get the units of micrometers cubed, which I don't want. I want to get centimeters cubed, so I would just do simple conversion. So I can write it out, the conversion, as follows. So this would be my radius in centimeters instead of micrometers, and so I would just plug this r back into here, and then my answer would be in centimeters cubed, which is perfect, because now I could just simply multiply by rho, and then I'm going to get my answer in grams. But remember, I want to convert to kilograms because I want all of my units to be in SI units. So to convert this to kilograms, simply need to divide by 1,000. So after figuring out the mass of each dust particle, I plug it back in to here. So now everything is known in this equation. I could actually just solve for it. I know this, I know that, I know that. I could look this up on Google, just figured out that, and I can figure this out by looking at my textbook or Googling it. So let me scroll down. So it turns out I get n is equal to, actually n is about 0.9. So this can be interpreted literally as I need at least 0.9 electrons to cancel out the gravitational attractive force. But we know that electrons do not exist as, 0.9 of a whole electron. They exist like this. So not like this, they exist as a whole electron. So pretty much you just need at least one electron to cancel out the gravitational force. So let me just put the interpretation into some sort of perspective. So the mass of the electron is equal to 9.109 times 10 to the negative 31 kilograms. And if you calculate the mass of the dust particle, it turns out to be 1.64 times 10 to the negative 10 kilograms. So all I need to do is add one of these extremely tiny, things, they're called electrons, in order to cancel out this gravitational force. So how small is this electron? Let's see how many times smaller is the electron compared to the dust particle. So if I write this ratio, the mass of the dust particle divided by the mass of the electron, I get about 10 to the 21 kilograms. So I ignore these extra factors out in front because I'm only interested in the order of magnitude of how big the dust particle is compared to the electron, and it's 10 to the 21 kilograms. So how big is that? Let me just write out what 10 to the 21 looks like. It's just 1 followed by 21 zeros. So if I compare the dust particle and the electron, the dust particle is 10 to the 21 times bigger than the electron. This comes to show really like these tiny particles. I can't even imagine how small these particles are. I can't even imagine this number. I don't think anyone could imagine this number in their head. But these super tiny particles are capable of overcoming the force between two objects that are 10 to the 21 times bigger than them in mass. And to me, this is, pretty awesome. I hope you find it awesome too. And stick around for more videos. Thanks.